Hi, you may remember this from a previous video on tree diagrams and probability. It's a question about sweets in a bag. Jenny has 7 blue sweets and 3 red sweets in it. She picks a sweet at random from the bag, replaces it, and picks again at random. And you were asked to draw a tree diagram representing this situation and to use it to calculate the answers to these 4 questions. What are the probabilities that she picks in these 4 different ways? Well, you may remember that we drew a tree diagram like this. And obviously 7 blue and 3 reds, the probability on the first pick is 7/10 and 3/10 for red. And that doesn't change for the second pick because she has replaced the sweet back in the bag. Whichever one she chose, she put it back. And so the second pick has exactly the same starting situation as the first. And so the probabilities haven't changed. Now, this is an example of a very important idea in probability called independence. And what it's saying is that the probability of the second pick doesn't depend on the first one. They're independent. The second pick is independent of the first one. So the probabilities for the second pick remain the same as for the first. In other words, what happened in the first round doesn't affect the second round. Now, here's a similar question, but it's slightly different. Jimmy has the same bag with 7 blue and 3 red sweets in it. He picks a sweet at random from the bag, but does not replace it. Instead, he eats it, and then picks again at random. Once again, you're asked to draw a tree diagram and to do these calculations of probabilities. Well, what's the new situation? Well, the first pick is exactly the same as before, 7/10 and 3/10. But for the second pick, it's important to notice that there are now only 9 sweets in the bag. And how many blues are there in the bag? Well, he's just taken one. So that first probability is 6/9. And how many reds are there? Well, he hasn't taken a red first time, so there's still 3/9 there. Second round, he has taken a red, so there are still 7 blues. So probability of a blue is 7/9 in that situation. But he has taken a red, so there are only 2 left, 2/9. And you notice that all those probabilities are different from the first round, and they're different from each other. Very much what happens in the second round depends on what has happened in the first. So this is not independent. This is a dependent situation. Right, let's do the calculations along the branches. If you remember, we multiply along the branches. So the probability of getting blue is 7/10 times 6/9, 42/90. Probability of getting blue-red is that one, 21/90. Probability of red-blue, once again 21/90. The probability of getting 2 reds, 6/90. Do you remember? We do a quick check to see that that adds up to 1. It does. It adds up to 90/90, which is 1. Right, let's go to our question. What's the probability that he picks 2 red sweets? Well, that's this bottom row here. We've already seen how that works. Answer is 6/90, which we can cancel down to 1/15 if we wish. No red sweets. Well, no red sweets means that they're both blue, so it's this top situation. BB 42/90, which cancels to 7/15. At least one blue sweet. Well, that's got a blue, that's got a blue, that's got a blue. So we add those 3 together and see what that gives us. 84/90, 14/15. But if you remember, there's another way, because the only one that we haven't got in this list is the probability of 2 reds. So if we take that away from 1, we'll get our answer a little bit quicker. 1 minus 6/90 is 84/90, which is 14/15. Same answer, slightly quicker. 1 sweet of each colour. Well, it's either blue then red or red then blue. So it's these 2 added up. Let's do that quickly. 42/90, cancelling down to 7/15. And we've done it.